For the third part, we're going to be looking at the adiabatic saturation temperature. In this scenario, we have an infinitely long tube with a mass flow going in at a certain temperature and pressure, and a pressure and temperature coming out. And with that, we have a stream of water at the bottom of the pipe running through the whole thing. And this allows evaporation of the water, and since the pipe is infinitely long, we can assume that the pressure at the end is the saturation pressure of the water. Now, given that, we're going to be looking at this in a energy balance format like we did with the second part. In this case, we have a steady state, so we're going to be using enthalpy in equals enthalpy out. So first, we're going to look at enthalpy in, which is equal to the mass flow rate of the air times the heat capacity, or the specific heat, times the temperature in minus the reference temperature, which is just 0. So it'll just be temperature in, plus the heat of vaporization times the pressure of the water in times the molecular weight. Since in this case scenario with the enthalpy and the mass flow rate, we'll be looking at kilograms, and we'll be looking at kilograms per meters cubed, kilograms in all senses of the problem, unlike the second part where we were looking at moles. And that's going to be over the gas constant times the temperature. Now, to cancel out the mass of the air, which is kilograms of the air per second, we're going to have to use the total pressure times the average molecular weight, and we're going to multiply that inversely. So you have the gas constant R times the temperature times the pressure total times the molecular weight average. Canceling those out, and this just giving you a ratio of the pressure times molecular weight over the total. I won't waste time rewriting that. That's 0, that's that. Actually, I will rewrite it as in equals mass flow to air times the heat capacity times temperature in plus heat of vaporization times pressure in molecular weight of water times pressure total times molecular weight average. Now we're going to look at the enthalpy out, which is going to be done in the same format as the last one, just some minor differences. So you have the mass flow rate of the air times the heat capacity times the temperature out plus the heat of vaporization times heat of vaporization times this time the pressure of the water out times the molecular weight of water times the pressure total divided by the pressure total times the molecular weight of the average. And now, since it's steady state, we're going to set these two, set the two equal to each other. So you have molecular weight of the air times the heat capacity, temperature in, plus the heat of vaporization times the pressure of the water in times molecular weight of the water times pressure total times molecular weight average is equal to the enthalpy out, which is mass flow rate of air, times heat capacity temperature out, plus heat of vaporization times pressure of the water out, times molecular weight of water, divided by pressure total times mass molecular weight average. Now, given this, we can simplify first by eliminating mass flow rate and looking at our like terms: heat capacity, heat of vaporization, total pressure, and our molecular weights. Doing that, we can simplify our equation down to the heat of vaporization times times the pressure in minus the pressure of the water out, which is also the same as the saturation of the water. Times, forgot one piece, I'll just leave it on the outside, the times the molecular weight of water, which is equal to the molecular weight average times the pressure total, heat capacity, times the change in temperature. Now, given our final equation and given our equation in the second one, the only difference that can be seen is that this one is multiplied by the molecular weights on both sides. Now, this differs from the first one because in the first problems we were using joules per mole, moles per second, moles per meter cubed. Now, in this equation we were looking at mass flow rate, so we're using kilograms for everything. So all you need to do to make them the exact same is just multiply the top one by the molecular weight of water and the molecular weight average, thus giving you the same heat of enthalpy molecular weight times difference in pressure equaling the molecular average weight times the total pressure times the heat capacity times the difference in temperature, which is the same as the bottom, just slightly written different. You end up with the exact same equation set up.